All right, so today we're looking at an introduction to logarithms. Sorry about the alarm there. Probably had to change the battery. So for logarithmic functions, our definition from the textbook says that if we have positive numbers x and b, we define a logarithm as a function y equals log base b of x. And the way that it's defined is it's equivalent to b to the y equals x. So it's a little bit of a strange definition sometimes, or it might seem strange. But we'll talk about how to interpret this and how to use logarithms through the video. So here it says the function f of x equals log base b of x is a logarithmic function with base b. Okay, the base is that little number down there. In this case, it's just b. Log base b of x represents the exponent on b that yields x. Okay, so to try to understand what this means is I can actually use a simple question that I can ask any student, and they usually respond correctly. If I ask, what is the log base 3 of 9? What I'm really asking here is, what exponent do I need to put on the base of 3, on the number 3, to get 9? 3 to what exponent is equal to 9? And most students would then say, well, that's 2. 3 to the 2 is 9. And that's correct. So the log with a base of 3 of 9 is equal to 2. Okay, so as we said in the definition up above, 2 is equal to the log base 3 of 9 if and only if, and that means that statement is equivalent to the base b, which in this case is 3, raised to the y, which is 2, is equal to 9. So these two are equivalent statements, and you would say, well, this is a pretty simple statement right here that I've just made. The logarithmic equivalent of that is, the one in the box to the left. So these two are equivalent statements. So logarithms are, can be thought of as just exponents. The log base 3 of 9 is the exponent that you put on 3 to get 9, and that's 2. Okay, so let's get a little bit of practice here with problem 1.1. And this is a reference to the worksheet that we have. So this is just my first example. And then the 0.1 just means it's going to correspond to problem number 1 on the worksheet. Okay, so it says, write the logarithmic equation as an exponential equation or vice versa. So with the first 4 examples, we're going to write the logarithmic equation as an exponential equation. So this equation here. 3 equals log base 2 of 8. Okay, that if you don't have a lot of experience with logarithms, that might seem a little bit foreign. So we can write this equivalently as 2 to the third is equal to 8. All right, and I hope this statement is very, just like, okay, well, yeah, 2 to the third is 8. That's no problem. Okay, so what about the log base 10 of 10 equals 1? How can we rewrite that? The way that I like to write it is, or the way I like to think about it is, essentially, if you have a logarithm equal to something else on the other side, then you take the base of the logarithm, that something else that's on the other side, you raise it to, that's to the first power, equals, and then the argument, the input of the logarithm, that's 10. 10 to the first power equals 10. Okay, and that should be one of the most obvious statements we've ever, given there. And so that's equivalent to this logarithm. The log base 10 of 10 is equal to 1. What about the next one? The log base e of 1 equals 0. This is equivalent to, and feel free to pause the video, try to write down the equation yourself, and you see if you get it correct. That would be the base raised to the other side equals the argument. E to the 0 equals 1. That's a true statement, right? E to the 0 is equal to 1, and it's equivalent to that logarithmic equation. And then the last one for the logarithms is, okay, we want to write this logarithmic equation in terms of an exponential equation. So let me, before I give the answer to this, I would strongly recommend you pause the video and try it yourself, because being able to switch between a logarithmic equation and an exponential equation is very important for this section. You know, it's a very powerful tool to be able to solve more complicated questions later, and we're going to show examples of that later in this video, and coming up in the next couple examples as well. So the base of the logarithm, the other side, equals the argument of the logarithm. And the argument, that's just a word that means like what we're plugging into the log. In this case is 1/9. 3 to the negative 2 equals 1/9. And if you remember your negative exponents, you know, 3 to the negative 2 is just the reciprocal of 3 to the 2. And that's, you know, 1/9. So that's also true. Okay, so we can work backwards as well, or, you know, we can take an exponential equation and write it in logarithmic form. This is also a powerful tool to master. And so we would write the log with the base. The base of the log is going to be the base of the exponential part of the equation. That's base 10 of 1,000. That's the number on the other side, equals the exponent. Okay, and so again, we could ask ourselves, you know, if we were just looking at log part, you know, what exponent do we need to put on 10 to get 1,000? Well, that would be 3. Yeah, so this logarithmic equation makes sense. Maybe I'll skip one and do, okay, the log with the base of e of 7.389. These are from the textbook, so you know, I just pulled these examples. And since they use the approximately equal to symbol here, I'll use the approximately equal to symbol there. We could check this on a calculator. I'm not going to do that now, but you know, if you have questions about that, feel free to ask. And then finally, the last one, log with a base of 9 of 27 equals 3/2. And this one's a little bit more interesting here. I like this one because, well, yeah, what exponent do we need to put on 9 to get 27? This is a little bit more complicated of a question because it's not just a whole number, but we can show that 9 to the 3/2 is 27. Because if you remember your rational exponents, the 2 in the denominator of that fraction in the exponent could be treated as a second root. And so the square root of 9 is 3. And then we still have an exponent of 3. 3 to the third is 27. So we see that 9 raised to the 3/2 is equal to 27. Therefore, the exponent that you need to put on 9 to get 27 is 3/2. Okay, so that's correct. All right, a lot of good stuff there. All right. Now, there are a couple of logarithms that come up a lot. And the first one, the textbook, it's called the common log. The common log is just the log with a base of 10. And it's common enough that it gets its own notation. This is just the log of x. Basically, you don't have to write the base. If you don't write the base, if you just write log of something, and there's no base written there, it's assumed to be a base of 10. Just like if I were to write, this statement here, you assume that the index is 2, even if I don't write it. Okay, so same thing. There's another logarithm that comes up often enough in many applications called the natural log. And it is a log with a base of e. This has a special notation as well, since it comes up so much. It is ln of x, the natural logarithm. And it's the ln is for log naturel in French, so that's why it's flipped, but it's pronounced the natural log, ln of x. And so actually in example part G up here, we could go back and we could say that log base of e, we could write it as ln of 7.389 is approximately equal to 2. And then we could even go back to example part E and write just the log of 1,000 is equal to 3. I don't have to write the base because it's assumed to be 10 if I don't write it. Okay, so a little bit on the usage there. So let's go ahead and go to problem 1.4. So if you also wanted to pause the video, you could even work on problem 1 on the worksheet, answer problem 3 on the worksheet. But let's move on and we will talk about 1.4. So how do we solve this kind of equation? Log base 2 of 8 equals x. Well, we can actually just figure out what this expression is here. The log base 2 of 8 is the exponent that I need to put on 2 to get 8. And the exponent I need to put on 2 to get 8, or 2 to the what power is 8? That is just 3. So this becomes 3, and I'm done, right? X is equal to 3. Now, another way that we could have done this problem, because sometimes they're not that simple, is we could have used this equivalence up here to rewrite the logarithmic equation as an exponential equation. Okay, that's what we practice in problem 1.1. So I'm going to do the same thing down below. How do we rewrite this logarithmic equation in exponential form? We would write the base, whatever's on the other side of the equation, so that's x, equals the argument. And now notice it becomes a little bit clearer, the question here, 2 to the what exponent is equal to 8? And we know 8 is 2 to the third, and so we can see there that x must be equal to 3. So let's try that again with the second part of this problem. Let's write this in exponential form, or as an exponential equation. This would be the base raised to the other side equals 1 over 25. Now what can we do? X to the negative 2 is just 1 over x to the 2. And if we zoom in real close there, what number squared is equal to 25? Right, you can see that there's a, this equation is equivalent to x squared equals 25. So what number squared is equal to 25? There are actually two solutions to that equation. X equals negative 5, because negative 5 squared is positive 25, and x equals positive 5. But we'll disregard the negative solution, because if you go back to the definition of a logarithm, it said that b, the base of a logarithm, must be a positive number. Okay, and so since x right now is in the base of the logarithm, its only solutions, the solution must be positive. A base can't be negative. So then x equals 5 is our solution. Let's try the next one. Ooh, this is a nice one. The natural log of x equals 1. Well, we just learned that the natural log is a shorthand notation for the log base e. So we can rewrite this problem as the log base e of x equals 1. We rewrite this in exponential form. The base raised to the other side equals the argument. And so x is just equal to e. The solution here is e. And we can plug this one in here just to check. Let's go ahead and plug e back in for x here. And so our check here would be just to plug in. So the natural log of e equals, and let's verify that it's equal to 1. Let's rewrite the natural log of e as the log with the base of e. And then it brings up the question, what exponent do I need to put on e to get e? Well, e raised to just the first power would return e. We just put the exponent of 1. So the natural log of e is 1, therefore e is our solution to the equation. Okay. All right. And I'll leave that one there for you to try on your own. You can ask me about it in class if you want to know the solution. Okay, so the domain of the logarithm, problem 2.5. So now after we've completed 1.4, you can try problem 4 on the worksheet. We're moving on though to 2.5. So this corresponds to problem number 5 on the worksheet. We want to find the domain of a logarithmic function and write the domain in interval notation. So we go back to the definition of a logarithm, and the argument of a log, or this logarithmic function, was x. And notice that we were told that x was a positive number. The domain of a logarithmic function, or the domain of log of x, is all numbers x that are positive, larger than 0. Therefore, we want the argument here to be larger than 0 as well. Okay, so we need to find out what values of x would make this argument larger than 0. The best way to do that is just to write the argument, set it larger than 0, not equal to 0, larger than 0, and solve for x. Here we would subtract 12 on both sides, so we get 4x is larger than negative 12, and then divide by 4 on both sides, x is larger than negative 3, and in interval notation, we know that that's negative 3 to infinity, not including negative 3, so we put a parentheses there. Okay. Try part 2 on your own. Pause the video, try part 2 on your own, and then we can check the answer together. So what do we do? Take the argument 2 minus x and set it larger than 0. I'll solve this by subtracting 2 on both sides. So negative x is larger than negative 2. Then I'll have to divide by negative 1 here, or I can divide by negative 1. And whenever you divide in an inequality by a negative number, you need to flip that greater than symbol. Now it becomes a less than symbol. That's one of the rules of inequalities. And so we get x is less than 2. And so we get all numbers less than 2 are all numbers from negative infinity to 2, not including 2. And so the reason I said earlier and tried to stress not to use the equal symbol, where that greater than symbol should be, is because if you use the equal to symbol, you might miss where that inequality flips, and you might think that the domain is from 2 to positive infinity. So it's better just to use, more accurate to use, the greater than, and if it ever has to flip, then it becomes a less than symbol. All right. Logarithms actually have a lot of cool properties. And problem 3.2 is, just covering those a couple of those properties. So first, I'll write the logarithm, this property backwards. And it says that if you add two logarithms, say the log with the base of b of m and the log with the base of b of n, how do you add two logarithms together? Well, if they have the same base, you can add them together and they become a single logarithm with the same base, but the argument becomes m times n. You multiply the arguments. Okay. The sum of the logarithms is the logarithm of the product of the arguments, if you want to put it in words there. Of course, this works backwards if you want to think about it this way as well. This is how they were given in the textbook, so I just copied them down. But if you have a logarithm of a product, you can also break that into a sum of two logarithms. So let's take a look at how this works. And I'll just do it in one step here, nice and simple. These two logarithms are being added together. They have the same base, so we can add them together. They become the log base 2 of 35. And you'll notice that sometimes I put a set of parentheses for the argument. That's not really necessary in this case. I could have left off the parentheses, just as long as it's clear that 2 is the base. I write it a little bit smaller and a little bit lower as a subscript, and then of 35. When you want to write parentheses, just to give a little bit of notation kind of advice here, if you want to write, or when you need to write parentheses, is like when you have multiple terms in the argument of the logarithm, like in the example below, x plus 2 is in the argument. If you wrote it without the parentheses, it would look like the natural log of x, and then outside of the logarithm plus 2, which we don't want because we need this. Okay, so how do you subtract two logarithms? Well, if you understood the addition one, then the subtraction one is not too much, more complicated. You would divide the arguments. So the natural log of x plus 2 minus the natural log of x becomes the natural log of, I'm using the same base here because those are the natural logs are all base e, and the x plus 2 goes in the numerator, and then the x, the argument of the second logarithm, the one that we're subtracting, its argument goes in the denominator. Okay. Okay. Now there's this kind of cool rule here with logarithms. If you take the log of an exponential expression, meaning log base b of m to the p, m has some exponent p on it, you can actually move this p to the front of the logarithm, and then it becomes p times the log base b of m. Sometimes that's useful. A lot of times, actually, that's useful. Very useful. So that's a nice property of logarithms. We're not going to go into the proof of this, but we could prove that this is, in fact, something that we can do. So let's actually do the second of these first, just to make sure that we understand what's going on. So the natural log of 5 to the x, this x can come out to the front, and it would become, maybe I'll write a little arrow. It becomes x times the natural log of 5, and that's it. Okay, and one more example right up above. This one we can actually verify. If I go in this direction, the log base 2 of 4 to the 2, I could bring down the exponent and write this as 2 times the log base 2 of 4. And that's essentially the answer here if we want to just rewrite the expression using the properties. But if I wanted to go further, I could ask you, what's the log base 2 of 4? What exponent do you have to put on 2 to get 4? And that is 2. So the 2 in the front is this one here. And then the log base 2 of 4 becomes 2. And so this is equal to 4. If I go in the other direction, I could have written this as the log base 2 of 4 squared is actually 16. And then I could ask you, what's the value of this logarithm here? What exponent do I need to put on the base of 2 to get 16? And we know that 2 to the 4th is 16, so that would be 4. And so, yeah, this little magic trick here that we have of moving this 2 out to the front, it ended up getting us 4, which is consistent with what we would have gotten doing in a different way. So that's nice. When I first learned logarithms, I remember I used to think that these rules were just kind of strange, and so I used to try to play with the rules to try to show that one of them was false. Kind of like how we're doing here. We're doing a problem in multiple different ways, but then every time I would get the same answer. And so eventually I just gave up and believed that the rule is true. We can see a proof. I mean, I can now, we can write a proof for this rule. But back then I didn't know about the proofs. Okay, so here's a couple more properties of logarithms. Oops. And this video might be a little lengthy, so feel free to pause the video and go do problem 2 in the worksheet. And maybe you can stop watching the video here and then come back to it and watch the rest later. But if you've got more endurance here, let's go ahead and continue. So there are more properties of logarithms. These are in the textbook, they're called fundamental properties of logs. And for any base b, the base we said needs to be greater than 0. The base can also not be equal to 1. You can tell me if you see me in class and why the base can't be equal to 1. Feel free to share that with me. I mean, I know why, but I'm not going to go into it because I don't want to make this video that long, or as long as it's longer than it's going to be. So let's go ahead and give these 4 properties, and we won't explain actually each one of them, but maybe we'll come back and explain them later. So this one here, you should be able to answer this one. What is the log base b of b? What exponent do I need to put on b to get b? The answer is 1. Because if you were to rewrite this using our definition from the first page, or our equivalence between logarithmic equations and exponential equations, this would become b, the base of the logarithm, raised to the other side, the first power, equals b. And that is a true statement there. B to the first power is b. So the exponent I need to put on b to get b is just 1. What about the next one? You should be able to answer this one as well. What exponent do I need to put on b to get 1? This is one of those rules. It's 0. Because remember, b to the 0 is equal to 1. Anything to the 0 is equal to 1. That's a common statement that you hear. I mean, when we say anything to the 0, here at least we're talking about any positive number raised to the 0 equals 1. That's definitely true. Okay, next one. This is the one that we're not going to explain too much. But the log base b of b to the x, here if I want to distinguish the argument, is there. What exponent do I need to put on b to get b to the x? That would be x. And one way to think of it is that students, or that as Jenna mentioned, is that these cancel each other out. A logarithm with the base. So the log of an exponential equation, or I'm sorry, the log of an exponential expression, if that exponential expression has the same base as the base of the log, then they cancel each other out, and all we're left with is the exponent. Okay, that's one way to think of this rule here. And so if we use the equivalence statement here, we would get b to the x equals b to the x. Okay, nice. And we can reverse the order there. If we have an exponential expression whose exponent is a logarithm with the same base, then we just get the argument back. Okay. And what we have in front of us here, this is an exponential equation. So we can write it in logarithmic form. We would write the log with the base of the exponential, that is b, of whatever's on the other side, that is x, equals, and then the exponent, which is log base b of x, and we get this true statement. Okay, maybe we'll talk a little bit more about these two a little bit later. Maybe. Okay, yeah. And then one of the last formulas here is the change of base formula. There's other rules as well that are in the textbook that I didn't include in this sheet because, well, like I said, don't want to make this video too terribly long. So the change of base formula, let's go ahead and do an example of that. And this one here is not going to come up on the worksheet too much, but maybe it'll help you, on the online homework, or it actually it can be used on the worksheet, but isn't necessary. So the log base 2 of 7, let's say, this change of base formula essentially just says that you can rewrite a logarithm with a different base. And so the log base 2 of 7, a lot of calculators will not do log base 2. My calculators, I have two cheap ones, one that I got at a dollar store and another one that I got at Walmart. They don't do log base 2. So I could not figure this out without the change of base formula, even if I had my calculator. So log base 2 of 7, the change of base formula tells me I can write that as the log base 10 of 7 divided by the log base 10 of 2. Pretty cool. You can just write the logarithm of the argument divided by the log of the base. Okay, so just as one more example, we can just do log base 3 of 4 or whatever, doesn't really matter. We can write this as the log of the big number of the argument divided by the log of the little number of the base. And notice that I just wrote log, the base is 10 there. And now my calculator can do log base 10. So, I can now compute this on my calculator where I couldn't, in the original form it was in. Now, this change of base formula has 3 alternatives that are given in the textbook. You could also write this as, if you wanted to, you could write this as log base 13 of the argument 7 divided by log base 13 of the original base 2. You can use any base you want. It doesn't have to be base 10. Commonly, you want to use base 10 because your calculator will do base 10. But if you wanted to, for some reason, write it as log base 13 of 7 over log base 13 of 2, you could, as long as you use the same base on the top and the bottom. And so another common, way that it's written out is the natural log of the original argument divided by the natural log of the original base. A lot of calculators, pretty much any calculator, will also do, a natural log. Calculators will do common log and natural log. Okay. And finally, we're getting to the end of our, problems here. So we'll do some example 3.67, which the 6, 7, indicates that you can work on problems 6 and 7. After seeing these, you should be able to attempt those and do them basically. Okay, so let's go ahead and do this. It says solve the logarithmic equation and check for extraneous solutions. So yeah, let's put together everything we've learned already. Notice that this logarithmic equation has 2 logs in it, but you can always just combine logs, assuming they have the same base. So let's go ahead and combine these logs. And I'm also going to write the base on there. We know it's 10 because we said if we don't write it, it's automatically 10. I'll just write it on there just for right now. So this would be the log base 10 of x times x plus 3. Remember we said to add two logarithms together, we would write them as a single log with the same base, but we multiply the arguments. That's what we get. And so we could write this again, log base 10 of, x squared plus 3x. Okay. Then now once, so this is kind of the strategy for logarithmic equations. If there are multiple logarithms, one way to do it is just to combine all of the logarithms into a single logarithm. And then we have a logarithmic equation with just a single logarithm and then something else on the other side, a number on the other side. So we can rewrite this logarithmic equation in exponential form. Remember that from the first page, the first thing we talked about? That would be now the base of the logarithm raised to the other side equals the argument. And now we have something, okay, we've been working on quadratic equations or second-degree polynomials in this class. And so we have x squared plus 3x minus 10 equals 0. And we can solve this. Now we're back to, algebra here. And so I'm looking for two numbers that multiply to negative 10 and add up to positive 3. Those two numbers are going to be negative 2 and positive 5, I think. Yep. And so this factors to x minus 2 times x plus 5 equals 0. And then I get x minus 2 equals 0 or x plus 5 equals 0. So x equals positive 2 if I add 2 to both sides, or x equals negative 5. So here I have two solutions, but I notice in the prompt for this problem here, it says, and check for extraneous solutions. Now I want to be very clear here that in these logarithmic equations, we can get numbers that seem to be solutions. We got two solutions here from this equation. But it turns out that one of them is actually not a solution. It's what we call an extraneous solution. Because remember that any solutions, yeah, you can check, you can plug in. So let's go ahead and check 2. We can plug that into, back into the original equation, and we would get the log base 10 of 2 plus the log base 10 of 2 plus 3 equals 1. This is the log of 2 plus the log of 5 equals 1. We know how to add two logarithms together. We multiply the argument, so this becomes a log of 10 equals 1. And since the base is 10, what exponent do we need to put on the base of 10 to get 10? That's 1. So this checks out. That works. But we don't get very far with the other solution. X equals negative 5. We tried plugging it into the logarithm. Try in your calculator. Find out what the log base 10 of negative 5 is. You're going to get an error, or you shouldn't get anything for that, because we cannot plug in a negative number into a log. So notice, it already fails with the first logarithm. The second one also would be, when you simplify negative 5 and 3, you get negative 2. And so it's going to fail there. And this is actually not a solution. It's an extraneous solution. We can actually scroll all the way back up to the beginning. And remember, it said for positive numbers, x and b. X, remember, was the argument of the log. The input of a logarithm has to be positive, larger than 0, right? We actually talked about it earlier when we said the domain needs to be, 4x plus 12 needs to be larger than 0. And so here, this x needs to be larger than 0. It cannot be negative 5. This one here, x plus 3, also needs to be larger than 0. So x needs to be larger than -3. It cannot be -5. Okay, so a lot of different ways we can show that x equals -5 is not a solution. Okay, so there's one solution to that equation, x equals 2. What else? Let's check the next one then. What if we have multiple logarithms, like 3 logarithms? There's actually multiple ways to do these problems, as you have seen in our class. That's true with a lot of different problems. But I'm going to keep it the same in this case. What I said was combine the logarithms, and then you're going to get a logarithmic equation equal to some number, and then just rewrite that logarithmic equation in exponential form and solve that equation. Okay, so let's go ahead and combine these two logarithms here. The natural log, they're both ln, so they should remain with the same base of e. The natural log of 87 divided by x. This is equal to the natural log of 29. Now, if we want to combine all the logarithms together, I'm going to have to subtract the natural log of 29. And I got to move them over all to one side. On the right-hand side, I'm getting 0. On the left-hand side, I'm going to get a subtraction of 2 logarithms. And we know how to subtract 2 logarithms. We would just divide the arguments, divide the first by the second. So this becomes the natural log of 87 over 29x. That 29 goes into the denominator. And maybe let me write it as a fraction this way. 87 over 29x equals 0. And at the same time, actually, let me write this natural log, just so I don't have to write it again. I'm going to write it as log base e. We mentioned that earlier. And so let me rewrite this logarithmic equation in exponential form. It's the base raised to the other side equals the argument. 87 over 29x. And actually, let's see, e to the 0, that's just 1. 87 divided by 29 is 3. Yeah, it is 3. So we would get 3 over x. And if we multiply both sides by x, we get x equals 3. Now we can check to see if this is an extraneous solution. The quickest way to check is just to make sure that this number here, this proposed solution, does not make any of the arguments less than or equal to 0. So if you plugged in 3 into this argument here, the argument would just be 3, which is fine because it's not negative. So x equals 3 is our solution. Okay. There is another way to do this problem. And I'm going to cover it really quickly. Sometimes giving too many ways, can be a little bit confusing because then there's just more stuff to memorize. But I'll give it just because, sometimes people say, well, there's an easier way to do that. Okay. Yes, there is. Let's go ahead and just cover it really quickly. And it's mentioned in the textbook as it's called the uniqueness property of logs. And it says, basically, if you have 2 logs that are equal to each other, and they're set equal to each other in an equation, and they have the same base, then that implies that their arguments must be equal to each other. M must equal N. Okay. And so how can we apply this? Well, in this problem, we would still take the same first step and say, as before, the first step is to combine these 2 logarithms. This would give me the natural log of 87 divided by x equals the natural log of 29. But rather than moving the natural log of 29 to the other side, we could say, well, we have a log equal to a log. They have the same base. And based on the uniqueness property, we can say that the argument on the left-hand side is equal to the argument on the right-hand side. Okay, you have to have a log on each side in order to be able to do this, and they have to have the same base. And there must be nothing else. If there was a +1 over here, the uniqueness property would no longer work. If there was a +1 that just carried on down here, it has to be just a log equal to a log, nothing else, and they have to have the same base. Okay, so very, in a sense, strict conditions in order to be able to apply this property. And so that's why I like the other method I gave earlier. Just put all the logs on one side, put everything on the other side, and rewrite that logarithmic equation in exponential form. That will work. Okay, so then we can solve this equation here, multiply by x on both sides to get 87 equals 29x, divide by 29 and you get x equals 3. All right, same answer. This is a nice wording of this uniqueness property. Equal bases imply equal arguments. Okay, nice. How do we solve an exponential equation with different bases? Well, we can actually apply a logarithm to both sides of this equation. So just consider this problem here. Let's say I had x cubed equals what's a cube number? 8, right? What number cubed is 8? Well, we know of a function called the cube root function, the cube root of x. And this function can be applied to this equation. We can say, well, we can take the cube root of both sides to get x equals 2. Yay. We solved for x by applying the cube root to both sides. Well, we just learned about a function called the log of x. Log base b. You can use any base. I'll use base 10 in this case. So we can actually apply the log to both sides of this equation. It's just like what we've been doing before, applying functions to both sides of the equation. I'm going to apply the log to the left-hand side and the log to the right-hand side. And we know from one of the properties of logarithms that we can take this exponent and write it out front. We can take this exponent and write it in front of the log. And so this equation that had exponents with variables. Now, how do we solve for the variable in the exponent? The way to do it is to apply a log to both sides, because the log property allows us to bring that exponent variable down and write it as x plus 1 times the log of 5 equals 2x times the log of 6. And keep in mind, I could have used any base b, any base log. I'm just using base 10 just because. Choose whatever base you like. It doesn't make a difference. And now I can distribute this log of 5 into those parentheses there. X log 5 plus 1 log 5 equals 2x log 6. With this kind of equation, then we want to move all the terms that have an x onto one side of the equation. So I'll subtract the x log 5 onto the other side of the equation. And we're going to have just a log 5 on the left-hand side, a 2x log 6 minus x log 5. And then we notice, wait a minute, we have a common factor of x there in both of these logs. So we can factor out the x. If we factor out the x, we're going to end up with 2 log 6 minus log 5. On the other side, we have a log 5. And then we just divide by that factor next to the x. So I'm going to divide both sides by 2 log 6 minus log 5. Kind of a lot of stuff there to divide by. That's how these problems go. And we end up with x equals log 5 over 2 log 6 minus log 5. If you want a nicer or another way, maybe not nicer necessarily, but another way to solve these equations, come talk to me in my office hours or leave a comment on the video if you'd like. Well, maybe not. That might not work. Leave a comment anyways. But come talk to me in office hours and I can explain it to you. It'd be hard to explain through a comment because of the notation. But there's another way to do this problem that is a little bit shorter, only slightly shorter. But if you're interested, feel free to check in with me. Okay, so there is that solution there. And I forgot to write, which problems this corresponds to in the worksheet, but look through the worksheet and you can figure that out. There's one problem that has exponential equations. Okay, and then the last part is graphing an exponential. And I'll do this really fast because this video is already 50 something minutes long. So basically, we want to plug in numbers into this exponential function. F of x equals 2 to the x is our example, but 3 to the x, 4 to the x, 5 to the x, they have roughly the same shape. You can graph them on Desmos or something. I'm going to start here by just finding f of 3. This is 2 to the third, which we know is 8. F of 2 is 2 to the second, which is 4. 2 to the first is 2. 2 to the 0 is 1. Now, f of -1, that one's a little bit more complicated. 2 to the -1, we kind of briefly talked about it earlier. That is the reciprocal of 2, which is 1/2. F of -2 is 2 to the -2, which is the reciprocal of 2 to the 2, or 1/4. 1/4 and 1/8. You can see as you go up the y values, they're just getting cut in half each time. Okay, so we can plot this function. And we get 0, 1, 1, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 3, 8, -1, 1/2, -2, 1/4, and -3, 1/8. And we can see that our shape would look something like this. And if we keep cutting this in half, it's going to get smaller and smaller and smaller, which I can't really picture well, but it's going to get closer and closer to the x-axis, but never actually touch the x-axis, right? Because if you keep cutting it in half, there's always going to be something, but it's just going to be super tiny. And so what we have there is actually a vertical asymptote, a horizontal asymptote at y equals 0. And that's the general shape of an exponential. Now for the logarithm, let's graph the log base 2 of x. And let's plug in the number 8. The log base 2 of 8. What exponent do we need to put on 2 to get 8? Oh, that's 3. The log base 2 of 4. I've chosen all of these inputs, these x values, to be powers of 2, so that these numbers work out nicely. So what exponent do we put on 2 to get 4? That's 2. What exponent do we put on 2 to get 2? That's 1. What exponent do we put on 2 to get 1? That's 0. 2 to the 0 is 1. And then what exponent do we put on 2 to get 1/2? Well, we need to do the reciprocal of 2, which would be a negative exponent of -1, and so on. You can reason the other ones exactly the same way. And so now we graph that function, g of x. So this is f of x. G of x, I'm actually going to graph it in blue. And so we get 1, 0, 2, 1, 4, 2, 8, 4, 5, 6, 7, 8, 1, 2, 3, 8, 3, 1/2 -1, 1/4 -2, 1/8 -3. And so we see a very similar behavior here. It does not cross the y-axis. It just keeps getting really, really close to it. My picture keeps showing like it's crossing. It does not cross, so let me see if I can. Something like that. Of course, these are hard to approximate for really small values. And then this function here keeps increasing. It increases actually very slowly, but it does continue to increase. And so the logarithmic function has a vertical asymptote at x = 0. And notice the domain. So the log, let's say, g of x equals the log base 2 of x. The domain of g is 0 to infinity. The range of g is equal to -infinity to +infinity. The domain of f, we can see the domain here is -infinity to +infinity. The range of f is equal to, you can see again, the lowest value it attains is 0, or that it approaches is 0. It doesn't actually attain that value, and it goes up to +infinity. If you notice, these two are just reversed, right? The range of f is the domain of g, and the domain of f is the range of g. And we saw this before when we studied inverse functions. It turns out that the logarithmic function is the inverse of the exponential function. They're inverse functions, right? So really we should even write g of x. Instead, we should write f inverse of x equals log base 2 of x. We can write g of x as the inverse of f. And so if you remember, we briefly also talked about what happens when we compose two inverse functions. If you plug in the inverse of f into f, we just get x. And that is why earlier, let's do a new color, if I say f of x is, let's say, b to the x, an exponential function, and f inverse of x is equal to log base b of x, well, what would I get if I do f of f inverse of x? I take the function f, which is an exponential. It's b raised to some exponent. I'm going to raise it to f inverse. This would be b raised to the log base b of x. If these two, in fact, are inverse functions, then I should just get x. And I can compose them the other way, f inverse of f. F inverse is the logarithmic function, the log with the base of b of, the input is going to be f. F is the exponential b to the x. If these two are in fact inverses, I should just get x. Let's take a mental picture of this here. And go back up to these fundamental properties of logs, which we said we might come back to. And we see this one here is that one there. And this one here is that one there. These properties are due to the fact that exponentials and logarithms are inverse functions of each other. Okay. So I hope that was, sorry for going a little quick there. I need to put my kids to bed. So I need to end this video now, but we've covered everything we were going to cover anyways. So, feel free to rewatch the video. Leave a comment though on the video if you liked it, and feel free to subscribe to the channel. Yeah, I'm going to try to put out videos for the other worksheets as well. Okay. Yeah, I wish actually we had more time to cover more graphs of exponential functions, or exponential and logarithmic functions, but with the basics that we did today, we will now be able to graph other functions, because other functions are just going to be transformations of exponentials and logarithmics, right? We talked about, shifting a graph downwards some number of units. So that's what this represents. We can shift the graph to the right or to the left. We can reflect a graph across the y-axis, scale it vertically, or do all sorts of things, scale it, reflect it, and then shift it. And so if you remember our function transformations lesson, then you won't have too much trouble graphing the other graphs on the graphing portion of this worksheet. All right. Hope you liked the video, and I'll see you next time.